today we will be discussing about an important application of op-amp, that is as a comparator. So, the comparator compares a signal voltage on one input of the op-amp with a reference voltage at the other input, and the op-amp will be acting in an open loop. So, the main principle of the comparator is that it compares two voltages which are given at the two inputs of the op-amp. So, let us take one example of a comparator. Here the op-amp is having two voltages, as we can see here. The signal Vi is a sinusoidal signal, for example, we are taking, and this is time varying, that is taken at the positive terminal of the op-amp, and the constant reference voltage is 1 volt reference voltage, which is taken in the negative terminal of the op-amp. Now, the resistance R is there for compensating the offset currents. So, we are having basically the comparing that is going on in this circuit. If we now see the two terminals, that is positive and negative, we know that the op-amp output V naught will be given by the gain of the op-amp, because it is an open loop fashion it is working. So, we are interested in finding out gain V naught. So, it will be A gain of the op-amp multiplied by the difference voltage VID, that is the voltage which is available between these two terminals, that is the difference between these two terminals, if I name it as V1 and V2. So, VID will be equal to V1 minus V2. So, it is A V1 minus V2, that should be the output voltage. Now, this op-amp has one plus VCC and minus VCC supply voltages are to be connected to all the ICs of the op-amp, and we have earlier also discussed about saturation, that is the output voltage cannot go on beyond the supply voltage, which is typically plus 15 minus 15 for 741 IC. So, VCC and VEE will be plus 15 and minus 15 accordingly. So, the output voltage, even though we may be having a very high gain around 2 into 10 to the power 5 or in that order, we will not be it will not be physically possible to get such a high voltage, because the output will be saturated by this supply voltage. So, maximum voltage that is obtained practically is around plus 14 volt and minus 14 volt. These are the saturation voltages, a little below the supply voltages practically we obtain. So, the output voltage in no way or under no condition can go beyond 14 volt and below minus 14 volt typically. That point has to be remembered while studying about comparator. So, now coming back to the output voltage V naught, which is given by A into V1 minus V2. So, now if we consider the time varying signal Vi, it will be having a magnitude varying with time. So, starting if we do from 0, it will be going to positive peak and going down, and it will go down to negative peak and repeat. So, at any instant, if we consider the instantaneous voltage, and that has to be compared with the reference voltage, because we are taking here a reference voltage of plus 1 volt. So, at any point the output voltage will be determined by this difference input voltage V1 minus V2. At V1 is this signal. So, when this V1 is greater than this V2, that means the supply voltage is higher than the reference voltage 1 volt, the difference voltage will be now obtained as V1 minus V reference. And for example, suppose we are considering an instant where the input voltage is 3 volt, because it is a sinusoidally varying voltage, its voltage at any point is, say, we are considering as having a value 3 volt. then what will be the difference voltage VID? VID will be 3 minus 1, that is 2. So, output voltage V naught will be 2 into gain, but if the gain is although very high, if we will be getting only around plus 14 volt, but it will be having a saturated voltage if Vi is greater than reference voltage. So, let us consider a sinusoidal voltage like this, which is Vi, and the reference voltage is 1 volt, is this dotted line is 1 volt reference voltage, and suppose peak voltage of the sinusoidal input Vi is greater than 1 volt, we are considering that has to be considered practically in order to get both the positive and negative saturation. Now, for the portion when the input voltage Vi is less than reference, that means this portion from 0 to that point of 1 volt, we will be getting at the difference voltage VID as V1 minus V2, and V1 is the signal voltage Vi and reference voltage is 1 volt. So, for this portion it is less. So, what will happen is that we are finally getting a negative voltage, because Vi is less than 1. For example, it is 0.5, it will be minus 0.5. So, we are getting a negative difference voltage. So, the output will be negative, A times this VID will be V naught. So, V naught will be A times VID. So, this will be negative and it will be limiting to the saturation voltage around minus 14 volt for 741 IC. So, we are denoting it by minus V sat, that is the saturation voltage in the negative. So, that means for this portion from 0 to the point where it is less than 1 volt reference voltage, the output voltage V naught be saturated, will be saturated at minus V sat. So, this is the point, this is the reason. Now, as soon as Vi becomes greater than the reference voltage, from this point onwards Vi is higher than reference voltage. So, this value of VID will be now a positive quantity, because is Vi is higher than 1. So, we are getting a positive value. So, that means as soon as the input voltage Vi becomes greater than the reference voltage, we will be getting an output which is positive, but that will be also saturated, because it cannot go beyond the supply voltage 14 around voltage will be the typically obtained value at the V saturation. So, that around that 14 volt V saturation, but this is positive, we will be getting at the output. So, till the point when Vi again becomes lesser than V reference, this will be saturated at that V set voltage. And then again when it is less, when Vi becomes less than V reference, then again we will be getting a negative saturation. So, it will be jumping from the positive to the negative saturation voltage as soon as Vi becomes lesser than V reference. So, that is why it is jumping to this negative. Again this will be continuing till the point when Vi is still less, and as soon as it is greater than V1 reference voltage, V reference, then it will again become V saturation become positive. So, like that we will be getting a digital pulse, that is here we are getting a voltage between two discrete levels only, V saturation and minus V saturation. So, this is like a digital voltage we are getting, which is only in two levels instead of input voltage which is analog, which is a continuously obtained voltage, and at the output we are getting a digital pulse. So, this comparator is giving at the output a pulse like this. So, now one thing to be noticed here is that we are getting an output voltage, and that is here it is a non-inverting comparator. We are connecting this signal at the positive N, and the width of the pulse basically is determined by the reference voltage, because we can change the pulse width, that is the reason for which it is positive and the reason for which it is negative, that can be controlled by choosing the level of the reference voltage, because we can see that if reference voltage is now increased or decreased if we have a voltage above this voltage 1 volt, or if we have a even lower voltage, then the reason for which it will be positive and the reason for which it will be negative, that will be changed. So, now let us take such an example having a reference voltage negative. So, we are again taking this example, but we are taking a reference voltage minus 1 volt. So, if we have a now minus 1 volt as reference, what will happen is that again we will be considering that sinusoidally varying voltage Vi, and we have Vid is equal to V1 minus V2. This is V1 at the positive terminal, V2 at the negative terminal. But here V2 is a reference voltage which is negative, so that is 1 volt. So, ultimately it will become V1 minus 1 volt. That means it is becoming V1 plus 1 volt. So, now what will happen when Vi is greater than 1 volt, suppose Vi is greater than 1 volt, here this will be positive quantity, then we will be getting the positive saturation voltage that can be seen here. We are having this input voltage Vi given by this sinusoidal voltage, and reference voltage is negative minus 1 volt. So, this is reference voltage. Now, for the portion starting from say 0, I am starting from here. So, for the whole signal up to this point, Vi is higher than V reference minus 1 volt. So, if this voltage is higher than this minus 1 volt, we will be getting a positive saturation voltage which will be around 14 volt for 741 IC. So, this saturation voltage Vsat is obtained from 0 onwards till the point when it becomes lesser than minus 1 volt. From this point onwards, it is negative direction and it is lesser than minus 1 volt. So, the moment it becomes lesser than minus 1 volt, so what will happen is that now Vid is equal to V1 minus V2, that is equal to Vi minus V reference, but V reference is a negative voltage minus 1 volt. So, it is Vi plus 1. Now, the input voltage is, for example, say minus 3 volt, it is lesser than minus 1 volt reference. So, what will be obtained? That becomes minus 2 volt. So, the output will be negative and it will be saturated to the V saturation negative, that is around minus 14 volts. So, the moment it becomes lesser than V reference, the output voltage jumps to minus Vsat, this is minus Vsat, so this is the minus Vsat voltage around minus 14 volt for 741 typically. So, it will be continuing like that, again the point when it becomes the Vi becomes higher than V reference, again it will be jumping to V saturation in the positive direction. So, here we are getting again a digital voltage, that is it is jumping between only two levels, plus 14 and minus 14 volt. So, here we have seen one difference from the earlier one. If we consider the width of the pulse, that is the portion for which it is positive and the portion for which it is negative, that is not same. This pulse width for the positive one and pulse width for the negative one is not same, it is not symmetrically positive and negative. So, that can be varied by varying this V reference voltage. That example we have seen. Now, if we consider a comparator, that means although we are getting a pulse type of voltage or the digital voltage, we are not getting the voltage having equal positive and negative portions. Now, if we want to get an ideal pulse having equal positive and negative portions, that means for equal time the pulse should be positive, that means V saturation should be V saturation should be there for equal amount of time with minus V saturation, that means V saturation and minus V saturation voltage which are there, they should be existing for equal amount of time. For if we consider say time period t, then for t by 2 it should be positive V saturation and for t by 2 it should be negative V saturation. That type of voltage if we want, then we have to consider a circuit where we will be getting this type of voltages, and that will be possible if the reference voltage is made 0. So, let us take one example of that type of zero crossing detector. Means this circuit which we are going to discuss, it will be able to detect when the input voltage crosses 0 and in what direction. Input voltage is a sinusoidal waveform we are taking, Vi is sinusoidal and Vi is a voltage which is crossing 0 for after a certain amount of time, say t by 2, say this is t by 2, this is t, this is the time period. So, the moment at t by 2, that moment if we consider, it will be crossing 0, this is the 0 line, it will be crossing 0 from positive direction to negative, from positive to negative it is crossing 0, and at this t it is crossing from negative to positive. So, a circuit which is able to detect the moment when it crosses 0 and in what direction of the input voltage, that means we are trying to detect at what moment the input voltage, which is a sinusoidal voltage, is crossing the 0 line and in what direction, that is it is crossing from positive to negative or from negative to positive direction, that can be detected by a circuit which is shown here. So, here the reference voltage is 0 voltage, positive terminal if we see, it is having a resistance R and it is connected to ground, that is 0 voltage is the reference voltage at positive terminal. And the negative terminal of the op amp is connected to the input sinusoidal voltage, but there is a resistance R also which is connected in the positive as well as the negative terminal. The reason being that there is need for compensation of the input offset current, that is why this resistance is connected as well. Here one important point is to be noted is that there are two diodes which are connected in the input of the op amp, D1 and D2, and their connection is also in the opposite way, that means here D1 has PNN in this fashion and D2 has PNN in the opposite way connected. The reason for connection of these diodes is to limit the input difference voltage given as input to the op amp, because if Vi is very large, that may damage the op amp. So, in order to limit the input voltage, we are connecting these two diodes. What will these diodes do is that the conducting portion, when the diode conducts, it will be having a drop of 0.7 volt typically. So, the input difference voltage to the op amp will be limited to 0.7 or minus 0.7, irrespective of which diode conducts. That means, if this diode conducts or this diode conducts, correspondingly we will be getting a voltage drop either 0.7 or minus 0.7, and this resistance is there to limit the diode current. So, now we are having this circuit and our aim is to detect zero crossing. D1 and D2 are additional components which are known as clamp diodes, because it clamps the input voltage given to the input of the op amp, that is the difference voltage, which is clamped to 0.7 volt and minus 0.7 volt respectively. So, now if we are now considering a sinusoidal input voltage Vi, then what will happen as we have an instantaneously varying sinusoidal voltage at any point, if we consider and compare it with the reference voltage 0. So, if this is the voltage, say we are now comparing it with 0 voltage. So, that means as 0 is the reference. So, we will be having only two portions to consider, that is the direction only, whether it is Vi is positive or Vi is negative. In this positive half cycle, Vi is greater than 0. So, here we see where it is connected. So, if in the positive half cycle we consider and the voltages are such that this is V1, this is V2, difference voltage is V1 minus V2, but then we will have to now take care of the connection of the clamp diodes, because when Vi is positive, as it is greater than 0, this diode D1 will now be conducting. So, diode D1 conducts and the drop across this diode D1 will be 0.7. So, now the output voltage will be what? Output voltage is V1 minus V2 into A, because VID, which is V1 minus V2, now VID is minus 0.7, because this drop is 0.7 across this diode. This is 0.7, here positive negative 0.7, but as the difference voltage is V1 minus V2, so it will minus 0.7. So, minus 0.7 into the gain A, but that will be limiting to the saturation voltage around 14 volt, but negative saturation. So, we will be getting a negative voltage when Vi is higher than V reference, means in the positive half cycle. So, in the positive half cycle of the input voltage, we are getting negative Vsat. So, that means it is inverting, that is an inverting of comparator actually, and when the input voltage Vi is in the negative half cycle in this portion, then what will happen is that as this is now negative, this is 0. So, this diode D2 will be now conducting, because it is forward bias now, because now it is negative, this will be negative now. So, now the D2 will be conducting, and D2 conducts means 0.7 volt in this polarity will be positive here and negative here. That means, we will be getting 0.7 volt which is positive, and VID is 0.7 volt positive for this portion, VID is 0.7 volt. So, output voltage will be positive, but it will be saturated. So, we will be getting output voltage V0 and positive Vsat, that is around 14 volt. So, for this portion when this input voltage is negative, we will be getting a V saturation in positive direction. So, here this is the constant V saturation voltage, again it will be changing to V saturation negative when it crosses over to the positive half cycle again. So, now one point to be to notice here is that the circuit here is able to detect the moment when the input voltage crosses 0, because at this point the input voltage crosses 0, and at that point the output voltage jumps from one saturation level to the other, that is from negative to positive or positive to negative. Here it is crossing 0, again it is changing from positive to negative, and the direction of the crossing, either it is from positive to negative or from negative to positive, that can be also detected from the output voltage, because at this point when the V saturation is jumping from negative to positive, correspondingly Vi is changing from positive to negative, that means it is crossing 0 from positive to negative direction. The moment when it crosses 0 from positive to negative direction, the output voltage V saturation jumps from negative to positive, and similarly when it crosses from negative to positive, V input crosses from negative to positive, then at that point the V saturation jumps from positive to negative. So, we can now detect the moment when it crosses 0 as well as the direction of crossing 0, either positive to negative or negative to positive. The positive that can be detected in the circuit by observing the output voltage change, and the time period for which V saturation exists is same as the time period for which V saturation negative exists. So, T by 2, if we consider this is T by 2, this is T. So, this time period is also same. So, we get here a perfectly square wave at the output, that is a digital voltage at the output with equal magnitude of time or equal amount of time for which positive voltage is existing and negative voltage is existing. So, this is a proper square wave we are getting, and if we now see that this circuit although it is giving a perfect square wave, but there may be one situation where it is misidentifying zero crossing for a noise. That means, if as noise voltage is present, when the noise voltage also crosses 0, that can be also detected as a zero crosser for this circuit. So, that is one disadvantage basically. And another disadvantage, if the frequency of the input voltage is very high, that is, if it is very fast, the input voltage is changing very fast, then the output voltage may not be able to track that, because it will take some time, because the speed of the op amp is one important criterion. The output voltage also should change very fast in order to keep a track of this change of the input voltage, but that has some limitation. The speed of an op amp has to be considered, because it may not be very fast, it may not be so fast as to track this input voltage frequency. So, because of these two difficulties that is faced by this circuit of zero cross detector, we have to think about some other circuit which can tackle these two difficulties of detecting noise as the zero crossing voltage and to take care of the fast changing input voltage. So, we have another circuit which is known as Schmitt trigger. This is also a squaring circuit, but it overcomes the problem of slow switching of the output voltage and false output transitions due to noise signals at the out. So, this circuit, which is the circuit of a Schmitt trigger, is shown here. It is also an inverting comparator, but here instead of the reference voltage which we are taking as 0, here the output voltage is fed back via this feedback network R1 and R2 to the positive terminal of the op amp. So, it is a positive feedback again, and we have this input voltage V in, which is a sinusoidal voltage, and how it works, that has to be understood by considering the reference voltage. Here there are two reference voltages known as V upper threshold and lower threshold, V ut and V lt. So, there are two threshold voltages or reference voltages, V ut and V lt. If we consider this polarity of V in positive and here and negative here in the positive half cycle, then the voltage which will have to be compared, the reference voltage, is V lt or the lower threshold, and in the negative saturation it will be that is the lower threshold, and the positive saturation voltage V naught, it will be upper threshold. Now, what is this voltage V lt? If we consider, that is nothing but the voltage at the output into R1 by R1 plus R2, that we know, this is voltage division, but then what will be the polarity? Because now if we consider this V in, when it is positive, it will be comparing with the voltage which is available here, and this voltage is coming from the output voltage via this feedback network. So, the voltage here is output voltage, which will be either V saturation or negative V saturation. When it is positive, that is this point is positive, say, then it will be here negative saturation, because it is an inverting comparator. It will be comparing with this voltage, and the moment this voltage V in is higher than this threshold voltage V lt, then switching will be occurring. So, for example, let us take what will be the output voltage for a sinusoidal waveform like this. Now, let us take this V lt and V ut and calculate them. So, V ut is the upper threshold voltage when we have the output voltage V saturation, then output voltage V saturation will be giving a voltage V ut, which is equal to V sat positive into R1 by R1 plus R2, and when in the lower threshold, that is V minus V sat, that will be minus V sat into R1 by R1 plus R2, that is V lt. So, the moment when this voltage V in is higher than VUT, that is here we see here this is VUT, this is VLT, and the voltage magnitude will be equal because V saturation and V minus V saturation, these are equal, and R1 and R2 same resistive network we are considering. So, if Vi is less than VUT from this point to this point, then we will be getting what voltage, because here if we consider this is say V1 and this is V2. So, V1 minus V2 is the VID, that is the difference voltage, and V1 is this reference which is VLT or VIT minus VI. So, when VI is less than VUT, that is happening here, that is VUT is here, and for this portion VI is less than VI is less than V reference which is VUT. So, VUT minus VI, that is the difference voltage. So, we have this is higher positive. So, we get positive saturation voltage at the output. The moment when Vi is higher than VUT, then as this difference if we consider, this is higher, so it will be negative. Now it will be negative, and it will be limited to saturation voltage. So, it will be saturated to V sat minus. Then as soon as it becomes V sat minus, then again what will be the reference voltage here? It will be VLT. VLT is lower threshold voltage. It is VLT is equal to minus V sat into R1 by R1 plus R2. So, this is minus 14 around. So, it will be, that means a negative voltage VLT. So, this is shown by this negative voltage. So, as soon as this output voltage jumps to negative V saturation, we have a reference voltage given by the lower threshold voltage VLT. So, now during this portion when this is output voltage is V saturation negative, we are to compare with this reference voltage VLT, and from this point to this point Vi is higher than VLT. So, that means we will be getting a negative saturation voltage V sat minus throughout this portion, and as soon as Vi is lesser than VLT, then again it will be jumping to positive V saturation, and at the same time we will be having a reference voltage given by VUT. So, from this point to this point, when positive V saturation is the output voltage, then we will have to compare with the VUT, and as this has been shown that the difference voltage is dependent upon the difference between VUT and Vi. So, VUT is higher, so it will be continuing to be positive, and this will be repeated or continued. So, basically here we have seen one interesting aspect, that the output voltage is a square wave, perfectly square wave, and we have the output voltage versus input voltage. If we consider, we find a hysteresis, and that is shown here. That is, if we plot V0 versus Vi, then we see a hysteresis kind of a thing. That is, if we consider say V in or the input voltage. Now, this is the axis of the V in, this is the axis of V0. So, now when we have V in less than VUT, this is the positive B in the positive half cycle, this is the upper threshold voltage, because in the positive half cycle the output voltage will be V saturation, and that is shown here. This is V in is when V in is less than V ut, then we will be getting a V saturation, and then if we have V in greater than V ut, we will be getting the output voltage jumping from V saturation to minus V saturation, and here it will be continuing to be at minus V saturation for this whole portion till when you have V in less than V LT. So, when V in is less than the lower threshold voltage in this portion, then immediately the output voltage jumps from minus V sat to plus V sat. So, this is a complete hysteresis is obtained, and this hysteresis voltage is known as the difference between the upper threshold voltage and lower threshold voltage, that is VUT minus VLT is the threshold voltage. So, this is a very interesting aspect of hysteresis being observed in this Schmitt trigger. So, in this Schmitt trigger we have seen that we can get a hysteresis voltage, and that voltage is the difference between upper threshold and the lower threshold. So, for example, we suppose consider a circuit where we are using the resistance R1 and R2 as 100 ohm and 56 kilo ohm. Input voltage is a sinusoidal voltage whose peak to peak value is 1 volt, and a frequency and at some frequency which is not very much important, because we are going to find out the shape of the output voltage, and here the saturation voltage is plus minus 14 volt. So, this is the Schmitt trigger configuration where we are given the resistance values as well as the input voltage. So, if we find out what will be the lower threshold voltage and the upper threshold voltage for the Schmitt trigger, we can calculate the lower threshold and upper threshold. So, what will be the upper threshold voltage for this example? That is V saturation into R1 by R1 plus R2, and V saturation is given as 14 volt. So, positive 14 volt will be the V saturation positive, R1 is 100 and R2 is 56 K. So, 14 volt into R1 is 100 by 100 plus 56 is 56 K. So, 56,000 ohms. So, that is equal to 100 by 56,100, and if we calculate this value 14 by 561, so it will be almost equal to 0.025 volt. That means 25 millivolt is the upper threshold voltage, and lower threshold voltage will be just opposite in polarity, but magnitude is same. That can be verified. What is lower threshold voltage? That is minus V sat into R1 by R1 plus R2, and as V sat is same 14 volt for both the positive and negative, that is why it is minus 14 volt into R1 is 100 by same values. So, 561100, that means we get minus 25 volt. So, that is the V upper threshold and V lower threshold voltage So, what will be the hysteresis voltage? That can be also find out. The hysteresis voltage equal to V upper threshold minus V lower threshold, and that is equal to 25 minus minus 25. So, 50 millivolt is the hysteresis voltage, and if we plot the input and output voltages, V in is this one, that is it is varying between the peak voltage of peak to peak voltage of 1 volt. So, obviously this V peak will be 0.5 volt and this will be minus 0.5 volt for the input voltage, and the upper threshold and the lower threshold voltages are 25 and minus 25. So, 25, say for example somewhere plus 25 is plus 25 volt millivolt, but it is millivolt. So, it is not scale, I am just showing to illustrate this example. So, that is minus 25 will be, suppose here this is VUT, this is VLT. So, the output voltage, if we plot V naught, so it will be comparing with this upper threshold and lower threshold. So, this is the lower threshold and this is the upper threshold, this is the lower threshold. So, it will be between V sat, this is V sat, which is obtained as or given as 14 volt, and this is minus 14 volts, say. So, in between these two it will be varying, it will be like this type of waveform we will be getting. Of course, this half and this half are equal, its drawing is improper. So, these two halves are equal. We get a square wave between plus 14 and minus 14 volt with this example of threshold voltage and the resistance values. Now, in this comparator circuits which we have discussed till now, basically we have got output voltage digital, no doubt, but the magnitude of the output voltages are not very sufficient for driving a TTL logic circuit, because in TTL logic circuit, transistor logic circuit which are used for digital ICs, we require plus 5 volt or 0 volt as 1 or 0, we have to use these voltage levels. So, basically we need a circuit to limit the output voltage to around 5 volt. So, for getting that type of voltage limiter, so we have to now think about a circuit which will be giving the output voltage limited to a particular determined value. So, let us take one example of a voltage limiter circuit and see how the output voltage will be limited to some predetermined value, not to saturation voltage, because saturation voltage whatever we got 14 volt or negative saturation minus 14 volt is too high. So, such a circuit can be devised or obtained by using Zener diode and ordinary diodes. So, let us take this similar example of the comparator circuit again, but here we will be connecting a Zener as well as a normal diode. So, this is a R is a compensating resistance for compensating the, this R is compensating resistance for compensating the offset current basically, but the reference voltage is 0, we are taking that 0 crossing detector, reference is 0, but we are having a Zener diode as, and in this case we are taking two Zener diodes. So, this is the load resistance where we are connecting the output voltage. Now, in this circuit, as two Zener diodes are there, obviously their Zener voltages must be lesser than what you get at the output, the saturation, that is 14 volt, it should be less than 14 volt. Now, what will happen when we have the input voltage sinusoidal is given, this is V peak, this is minus V peak. Now, in the positive half cycle, let us consider when this is positive half cycle, this half cycle. So, this is the reference is 0 of course. So, the comparison will be giving an output voltage V saturation at V naught, and that will be negative V saturation, because it is VID is this V1 minus V2 is VID, and that is equal to 0 minus Vi. So, that is a minus Vi. So, we are getting here a negative output voltage which is magnified by this op amp gain. So, we will be getting at the output, if we consider V naught, if we consider for this, we will be getting, for this portion we will be getting a negative. But then what will be this voltage? This will be not saturation voltage, because as this Zener diode is connected, what will happen is that when it is negative, this diode is say D1, this diode is say D2. So, the reverse breakdown will be taking place in the case of the diode D2, because it is negative, P is negative, this is connected in the reverse direction, and as far as the diode D1 is concerned, it will be having the ordinary drop of around 0.7 volt, that is typical for silicon. That means, we will be getting the total voltage drop V naught as V Z2 plus drop D1, V D1, that is the diode drop of D1 plus the Zener voltage, which is the Zener voltage drop of the diode D2, because D2 will be reverse breakdown will be happening, there is Zener breakdown will be happening, it will be conducting, but here it will be normal conduction, because it is forward biased when it is negative, and that is happening in the region when this Vi is positive. So, we are getting this voltage as minus, this is minus. So, this voltage, if we consider this drop plus this drop with a minus sign, will be getting minus Vz, will be getting here for this positive half, we will be getting for this portion, we will be getting a minus Vz2 plus V D naught 1. By V D naught 1, I am meaning the normal diode drop in the diode D1, and Vz2 is the Zener voltage drop in the diode D2, because that is conducting as a Zener diode. This is for the negative half cycle. Then in the that is this negative voltage you are getting for the positive half cycle. Then what will happen in the negative half cycle? In the negative half cycle, this V1 minus V2 means 0 minus Vi, as Vi is negative, we get a positive voltage. So, we are getting at this point positive when this is negative, this is positive. So, we are getting a positive. So, now D1 will be conducting as a Zener diode, Zener breakdown will take place. We are assuming, of course, this Zener voltage is less than this V naught saturation, V sat 14 volt. So, now breakdown will be here in the D1, and D2 will be acting as a normal diode, ordinary diode, which will be having the normal diode drop of VD naught 2. So, this voltage we will be getting, that is in this direction we will be getting plus, here this is. So, we will be getting a positive voltage V Z1 plus V T naught 2. So, we will be getting for the negative half cycle. So, it will be like this. We are getting, that means a limited voltage, not V saturation, but it is depending on VZ2 or VZ1 and VD0 for the two diodes, and it may be, say, if we take a Zener diode having say 5.1 volt Zener and 0.7 volt as the diode drop, we can get as 5.1 plus 0.7 5.8 volt around, not 14 volt V saturation that we were getting. So, similar circuit, if we consider only one Zener diode instead of this, suppose we are having now only one Zener diode, this has been removed, this has been removed, then in this case if we want to find out what will be the output voltage, then in the output voltage when it is in the positive half cycle, what we will be getting in the positive half cycle means when it is this is positive and that means we are getting a negative voltage, saturation voltage V naught, and this will be now acting as a normal diode. When it is in the positive half cycle, the output voltage is negative Vsat, and this will be acting, D1 will be acting as a normal diode. So, we will be getting a normal diode voltage drop which is 0.7 but negative. So, here we will be getting a 0.7 volt negative, and then when it is in the negative half cycle, we will be having a negative half cycle means this point is say negative, this point is positive, then at this point we are getting a positive Vsat means 14 volt positive, and this Zener diode is, suppose this Zener voltage is 5.1 volt Vz and Vd naught is say 0.7 volt, then we will be getting 5.1, when this is positive we will be getting this V naught as 5.1 volt. So, it will be like this one, this is 5.1 volt. That means, we will be getting, of course, these two voltage magnitudes in the two halves are not equal, that is minus 0.7 volt, this is 5.1 volt, corresponding V input was this one. So, it is an inverting comparator. When this is positive, we were getting a negative minus 0.7 volt. When it is negative, we were getting a positive 5.1 volt. This is 5.1 volt. So, the overall voltage is like this. So, here we are showing an example where we can reduce the output voltage or limit the output voltage, which in the ordinary zero crossing detector we were getting around V saturation voltage of 14 volt or minus 14 volt in the minus V saturation, but this is a too high a voltage. In order to use it for digital circuits, we require a voltage which should not be beyond around 5 volt for a plus for a 1 level or high level, and the 0 level is around 0 voltage that we should get. So, that means whatever the zero crossing detector comparator was giving, it was a voltage which was too high for use in the digital circuits. So, here in zero crossing detector we were having an example of the sinusoidal to square of conversion. That means, we are getting an analog to digital type of conversion of the voltage. Given an analog input, we are getting a digital output in the zero crossing detector that we have seen, but that output was too high and it was almost not practical to use it in digital circuits directly. So, we had to devise some other method, and by using the Zener diode we could limit down the output voltage to an usable level of around 5 volt, around we can limit it by using or choosing the proper Zener diode. Depending upon Zener voltage it will be having the output value. So, if we choose around 5 volt Zener, exactly precisely that voltage Zener diode, we may not get the exact 5 volt, but near around 5 volt for use in digital circuit we can get by properly using that proper specification Zener diode, and that can be used for digital circuits. So, this was an example where we have seen that an analog voltage or a sinusoidal voltage what we were using could be converted into a digital pulse, and by using proper components like Zener diodes we could even get down to that usable digital voltage level and use it for our practical digital circuits. So, that is one big use of comparator circuits which we can use in our digital devices. So, whenever we want to have a digital voltage from an analog sinusoidal voltage, we can use that type of comparator like zero crossing detector. So, in today's class we have seen the basic circuit of comparators which compares the voltages at the two inputs of an op amp, and we have seen how the output voltage switches